All right, now let's do some examples with force, Coulomb's force. Sorry, trying to make sure I have the pen working. With actual values. What I want you to do is pause the video, look at the first example. So we have 3 charges in a line, and we want to know what the net force is on the 5 nanocoulomb, that small n. So just to remind you, little n is 10 to the negative 9 coulombs. Okay, so pause it and come back, and we will solve the first example. Alrighty, so what do we have here? I have a positive charge being attracted to that negative charge and also being repulsed by that positive charge. So this is much the same as the example that we did with the charges on the square, but now we just have actual charges involved there. So let's see what we have. I'm going to define that way as positive. Go ahead and do up, why not? Just so that leaves out any negative signs. So the sum of my forces in the x, I can pull k out, and I can pull, let's call this 2, 1, and 3. So I can pull q1 out, and then that lets me go q2 over r squared. So because they're different distances, I'm going to go ahead and put in the actual distance. So 0.5 squared plus, not minus, I've defined to the left as being positive, and we've already decided what direction those vectors are going to go. So plus q3 over 0.8 squared. Now I can do something to make my life a little bit easier. Remember, k has this value of, I'll write it bigger, 8.99 times 10 to the 9th newtons meters squared per coulomb squared. So I can look at these 2 charges here. They're nanocoulombs, and they're all both 10 to the negative 9. So I have what? I have kq. I want an eraser in the worst way. Hold on a second. Now I want my OneNote to work so we can actually use a lot more space. Okay, I'm done complaining. Let's just write this out over here. So I have k, which is 8.99 times 10 to the 9th. And my q is this q1, so that is 5 times 10 to the negative 9. If I look at this multiplication here, at 10 to the 9, those 2 quantities cancel out. But in here, I still have 4 times 10 to the negative 9 over 0.5 squared plus 3 times 10 to the negative 9 over 0.8, sorry, 0.8 squared. So let's put that in our calculators and see what we get. So after putting it in my calculator, what do I get? I get 929.9 times 10 to the negative 9. Otherwise known as 10 to the negative 9, 10 to the negative 8, 10 to the negative 7. So I can either write it this way, or I can write it this way. I can write 930. We'll just round. Nano newtons. It's up to you. So you can write it with scientific notation or start getting used to writing nano and micro. They're units we're going to deal with a lot. right, so pause this, and let's now take a look at problem number 2, where we have these charges arranged, and what do we want? We want the net force acting on Q3. So pause and come back. Okay, so the first thing I want to do for myself is make a note on my drawing. I've been given these distances, so I know that this is 0.1 meters. And where's this distance? Oh, they're both A. I forgot about that. Yep, 0.1 meter. And Q2 is a -2. And Q1 is a +5. And Q3 is also +5. The first thing I look at, I'm like, okay, we know one R. Let's go ahead and solve for a different R. I want a different color. I know that this distance here, from here to here, I have my nice handy dandy right triangle, so I'm going to have the square root of 0.1 squared plus 0.1 squared. Which is going to give me the square root of 0.02. That's known as the square root. Come on, 0.02. Okay, now I need to notice a couple of things. Let's see what our force vectors are going to look at. Let me do a different color pen. You can clearly see that. For the positive to the negative, I'm going to have a force vector going like this. So this would be force 2 on 3. I have a positive and a positive, so I'm going to have a force vector coming out like that away. That would be force 1 on 3. It's repulsing. One of the ways I tell people that you can kind of work your way through what each of these guys is doing is imagine nothing else is there, and you're asking yourself, what direction is that charge going to go if I lift my finger up off of it and let it flee? So if I have two positive charges, it is going to be repulsed by that positive charge and make it flee the opposite direction. Okay, so that gives me some trig I need to do. I can look at this. What do I know about this? All the same size, same size sides. So that tells me that this is going to be a 45-degree triangle. 45, 45. Cool. Which makes the math a little bit easier because now, unlike the last time, let's see, I have if I make this my axis, I have a vector coming this way and a vector coming this way. So what am I going to do? I'm just going to go with the standard up and to the right is positive. And this means that I'm going to need a sum of forces in the x and the y. So my sum of forces in the x, what do I have? This is a 45-degree triangle, or 45-degree angle. That's just drawing that line. If I continue this kind of like equal and opposite thing, you can see that that is going to be the same angle. So I have force 1 on 3 in the x. So I want the x component of this triangle. It's touching it. So cosine of 45, so cosine theta. Now the other vector is going in the opposite direction, so minus force 2 on 3. And that will give me my net force there. And now my sum in the y, well that's just kind of handy because there's only the 1 going in the y, is that I have this force 1 on 3, opposite side, so sine of theta. Now I can add them up. So force 1 on 3, let's see, I'm going to have, oops, got an itch. My forces in the x then are going to equal 1 on 3, K, Q3, yeah, we'll go ahead and write it. I don't have enough space. So Q3 is 5. Let's remind you, micro is 10 to the negative 6. 5 times 10 to the negative 6 times the other charge, Q1 on 3. Q1 is, oh, they're both the same. That's right. 5 times 10 to the negative 6 times cosine of 45 minus force 2 on 3. So minus K Q2, which is 2 times 10 to the negative 6 times 5 times 10 to the negative 6. Oops, I forgot my r squared. Okay. Let's, I gotta erase. Erase, erase, erase. That's what happens when I try to get things done too fast. Alright. I need the same thing. So K times my 5 times 10 to the negative 6 times 5 times 10 to the negative 6 over r squared. So square root of 0.02 squared and times cosine of 45. Cool. Then minus, now we'll bring it down here, minus K times 5 times 10 to the negative 6 times the other charge, 2 times 10 to the negative 6. And over that distance is the 0.1 squared. We'll just put that into our calculator. And then the force in the y, well, that is just going to be our K. And the only thing we have is the two same charges being repelled going up. So this time I'm just going to simplify it. 5 times 10 to the negative 6 squared. Divided by, well, it's still square root of 0.02 squared is just going to be 0.02. There's my r squared. And times sine of 45. And then my net force is just going to be, let's see, so force net is, remember, it's just Pythagorean, so now I have my force in the x and my force in the y. So if I want to know the force net, then I would have the square root of those two forces squared, right? Just Pythagorean. So square root of force in the x squared plus force in the y squared. And then if I want the angle of the net force, then I can use like tan theta. Let's see, and that's going to equal opposite over adjacent. So what are we going to have here? I could look at this. I'm going to have some component going out here, and then I have an up. So I'm going to expect that my net force is going to be like kind of coming up-ish over here. So I have to find what my x and my y forces are. So I'll have this piece, and I'll have this piece. So the angle then, tan theta, is going to be opposite over adjacent. So my force in the y divided by my force in the x. I put all of those values into my calculator, and that gives me the final answer for what's going on there. So the important thing, re-emphasize, do not put in the negative signs. First we define what direction things are going. It's just like last quarter. Once we've decided what direction of force is, and we define what direction positive is, we don't put in negative signs anymore. We just put in our values. All right? So the next one isn't going to be math intensive. It's just going to be kind of a fun, let's see how the concepts are sticking.